The sigma notation looks scary because in many science fiction movies, when scientists write some complicated formulas on the blackboard, they would have a lot of these sigma symbols on there, right? And it doesn't really help if somebody tries to explain that this is really you plug in 1 and you get 1 squared, and then you increase by 1 and you get the 2 squared, and so on and so on until you reach this top number. Unless if you have any experience with computer programming, there are something called for loops, and in Python or in JavaScript, once you know what this corresponds to, then it's easy to understand. However, I'm not assuming that you know programming, so let's try to just purely explain this in mathematical terms. So what is the sigma notation? Well, it's just a shorthand. It's just a way to write something that's long in a very compact way so that you can save trees and go green, you know. But not only that, if you use shorthand, then you can see some patterns that are harder to see if you did not write in shorthand. And one of the example problems we'll solve will actually tell us that. Okay. All right. So let's think about what sigma notation really is. I will try to explain it to you, but you may have to repeat this part of the video several times until you get it. So this n, which is called the index, is a number that starts from the bottom one and it keeps increasing by 1. So the n increases by 1 at a time. And while you do that, this function is evaluated. So when n is 1, 1 squared is evaluated, so you put 1 squared. When then you increase by 1, so n becomes 2, so 2 squared is evaluated. And then you increase by 1 again, so 3 squared is evaluated. And 4 squared, all the way up till you reach the last number. That's where you end. And so you get 100. Now, sigma here is a Greek letter S. It's a capital S in the Greek alphabet system. And the reason people use sigma is because we're thinking really of the word sum. What does sum mean? That means you add, right? So you're adding all these numbers that was produced by starting from 1, evaluating this function, and increasing n 1 by 1 until you reach this end. So that's what it does. And any kind of summation of numbers that follows some pattern can be represented using this sigma. So as you can see, rather than writing all this, which I usually say dot 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 notation, but if you write the longhand, it takes several pages. If you actually wrote this explicitly without saying dot dot dot, it may take an entire page, right? It takes time and effort, but look how simple this is. It's very compact, right? So that's why that's how this sigma notation works. Now, because of this, whenever you see any kind of formula for the sigma notation, like this one or this one, don't try to memorize them as formulas, but just think about what it means when it's actually in action. So here, if you have some constant in front of some an, so an is like a function of n. I might as well just say f of n as well, but it doesn't matter. So it's something that changes with n, and if you add it, and let's just say n starts from 1 and goes up till 50, whatever number. You can start from 2, it doesn't matter. But what's really important is that because this is a shorthand, to actually understand why it's possible to move the c outside, you actually have to write the longhand, which is that n is 1, evaluate, so you get c times a1. Then increase n by 1, so it's 2, evaluate, it's c times a2. And then evaluate c times a3, all the way up till up till c times a50. And then I wrote this addition too early, but sigma means you add. Okay, so add. Okay, and if you look at this, you see that c is a common factor of all these terms. So of course you can factor the c outside, and you get the following. Now, if you can see that this is again a dot notation, you should think about how to rewrite this in sigma notation, right? So put a c outside, but this one is the same thing as sigma of you're adding the a, and you can see that these numbers change and they increase by 1, right? So you have a n, and you get n equals to 1 until 50. So that's why you can bring the c outside. Same thing for this one. If you had an and bn, and let's say you're adding n from 1 through 20 or some number, then what would happen? Well, that's like n starts from 1, so 1, a1, b1. The next number would be a2, b plus b2, right? When you plug in 2 here. And then you add up until it reaches the last number, which is a20 plus b20. And then you can just gather the a's together and b's together, so you have a1 plus a2 all the way up till a20. And then plus b1 plus b2 all the way up till b20. And they can now separately be expressed using sigma. So this first one will be these numbers change. So those are like n's. So it's a n, where n goes from 1 through 20. And then plus this one, you can see that these change, and you go from so n is the changing number, and you go from 1 through 20. Okay. All right. So you can easily see that these formulas do work. I think the first challenging thing maybe is to try to express some given form in this sigma notation, especially when you have some pattern which is not so evident. So let me put a rather challenging question. So express 2 times 3 plus 4 times 5 plus 6 times 7 plus 8 times 9 plus all the way up till 100 times 101 in sigma notation. Okay, so how would you do this? Well, so the trick is to first think about the formula for these. Okay. You see that these are arithmetic sequences, so you can also just use an equals to a1 plus n minus 1d, or you can just do trial and error. This is like it's 2n. You can just say an is 2n. Then that gives you all these numbers, right? But perhaps you didn't see it right away, so let's just use this. So what is it? a1 is 2, because a1 is the very first one, and these are increasing by 2, right? So it's the common difference is 2. N minus 1 is just n minus 1, so that's 2 plus 2n minus 2, so that's just 2n. So we know that in general what you have is the very first number is 2n. Now if this is the very first number, then what's the next one? Well, there are two ways to do it. One is just name this one as b1, b2, b3, and so on. So in that case, like bn would be again, it's an arithmetic sequence, right? It increases by 2. So the very first number, b1, is 3 plus n minus 1 times, again, it's increasing by 2. So you get 3 plus 2n minus 2, which is 2n plus 1. However, you could have just seen this and say, hey, the next number is always 1 more than the previous one, and just say, okay, if the first number is 2n, you can just do 2n plus 1. Okay? And if you do that, then you're able to see that when n is 1, it produces this number. When n is 2, it produces this number. When n is 3, 3 times 2 is 6. 3 times 2 plus 1 is 7. So indeed it produces this one. And then you have to figure out when it produces that one. Well, 2n has to equals to 100. And that would happen if n is 50, right? So you see that this is the case when n is 1, plugged into this function. And this is the case when n is 50, plugged into this function. And therefore we have a pattern. This is the general form, and we are adding them where n starts from 1 and it ends at 50. So that's how you figure out the sigma notation when you're given a series. So you can write this long form in a compact way and save trees. Yeah, but this takes time and experience, so please try to do more and more exercises in figuring out how to change the dot 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 notation into sigma notations. Alright, let's move on to some more formulas. These two are pretty easy to see if you actually write down what it means. So first, this one means when k is 1, there's no k in here, right? So if you evaluate with k equals 1, it's just c. And when k is 2, again, this thing just evaluates to c. So this left side is really c being added over and over again until k counts up to n, which means in total n number of c's are added, and therefore when c is added n times, it's same thing as c times n. On the other hand, this means 1, when k is 1, this evaluates to 1, and then when k is 2, 2 evaluates to 2. So you just keep increasing k until it reaches n. So that's what you get. And to figure out why this is same as the right side, you do it like this. You have you think about this summation as s, and then you write the same thing, but this time you start from n minus 1, n minus 2, and you start decreasing by 1. So n, when you decrease by 1, is n minus 1, right? N minus 1, when you decrease by 1, you get n minus 2, right? And if you keep going down, at some point you're going to get 3, 2, and 1. Now, we agree that changing the order of addition doesn't change the value, right? So this will still be equal to s. So we're just going to call the sum, entire sum, as s. And we have two ways to write the same thing. And therefore, when you add them, let's see what happens. S plus s will be 2s. Whereas 1 plus n, 2 plus n minus 1 is 1 plus n, right? So you always get n plus 1 as the sum if you pair them, right? And at the end, n plus 1 is what you get. Now you have to think about how many n plus 1s you have, but it goes from 1 through n. So again, this is n of them. Therefore, this value would be n plus 1 times n, which is equal to twice the sum. And therefore, if you divide by 2, you get sum equals to n times n plus 1 over 2. So that's how you get this formula. Now, there are two more formulas, which, depending on your teacher, sometimes they tell you to memorize them. Sometimes they give a formula sheet for you. But it's not so hard to memorize. This is n times n plus 1 over 2 it's very similar to that one, right? But there's a 2n plus 1 over 3 multiplied to it. And this one also has n times n plus 1 over 2, but you have to square that. Now I have a separate video that proves these two, actually just this formula, but then tells you how to get the other one. And since it takes a lot of time, in this video we'll just accept that. If you're curious to know why these go like that, please watch the other video. Okay, so with these we can find out summations of more complicated ones. And here's an example. What is the sum of 2k minus 1 times k plus 1 when you add from 1 through n? Now for this one, it's very tempting to think that, oh, it's you're adding this one, so maybe this is same as sum of the 2k minus 1s and times sum of the k plus 1s. But unfortunately, such a formula doesn't work. And to really convince yourself that why this doesn't work, you just have to write them out, the longhand. So, you know, the reason that the sigma notation is hard is because it's written in shorthand, and therefore to understand what's going on, you have to be able to go back and forth what's really being done. So when k is 1, you have 1 times 2 as the very first term, and then when k is 2, it's 2 times 2 minus, so that's 3 times 2, and then you have 5 times, sorry, that's when k is 2, this will be 3, right? And then 5 times 4, and then 7 times 5, so on and so on. And that's definitely different than doing this, which is like 1 plus 3 plus 5 plus 7 times 2 plus 3 plus, see, because if you expand this, these are not the only things that you get a lot of the other ones too, right? So you should be convinced that you can't do that, which is very important. Not only you need to know what's possible for a sigma notation, you also need to know what's impossible. Alright, so given that, now what do we do? Well, recall that although we cannot break up products, we can break up additions. So what you want to do is you want to FOIL this out so that you end up with a notation that can be split, because these are additions and subtractions. So think of it like this. 2k times k is 2k squared. 2k times 1 is 2k. Negative 1 times k is negative k. Negative 1 times 1 is negative 1. And these are like terms, so you end up with sigma of k equals to 1 through n of 2k squared plus k minus 1. And now that these are additions, you can also think of negative 1 as plus of negative 1, right? You can break them up. That's actually a formula that we figured to be true, right? So here, if you have an addition, you can break it up. Okay? You have 2 sigmas. Okay? So going back, we can break this up into 3 sigmas. So let's see what that does. Sigma of 2k squared, k equals to 1 through n, plus sigma of k equals to 1 through n of k, and plus sigma of k equals to 1 through n of negative 1. And then you can also bring this 2 in front. So it's 2 times sigma of k squared, but we just did it, right? We just did the formula for the k squared, which is, hopefully you remembered it, but if you didn't, then you can go back to the video and figure out what it was. It was n plus 1 times 2n plus 1 over 6. Okay, and then the next one is n plus 1 over 2. And this one, if you're adding the constant and you're adding it n times, it will be negative 1 times n. And then you can simplify that, and that will be the answer. Yeah, so try simplifying that. I'll leave this simplifying thing to you because I want to really show you the last question. Here's the last question. Use the identity 1 over n plus 1 equals to 1 over n minus 1 over n plus 1 to compute this. And imagine how hard it would be to recognize this sum if you actually wrote this way. So if somebody told you, what is 1 over 1 times 2 plus 1 over 2 times 3 plus 1 over 3 times 4 all the way up till 1 over 20 times 21, then you wouldn't want to do it, right? It's just simply too much, right? But if you write this in terms of the signal notation, then you start seeing that you have this common function, and you think about various ways to represent this in a different way. And one interesting thing is that there's this identity that happens to be true. Now, how did somebody figure this out identity? Well, the thinking goes like this. If you have something over n, and if you have something over b, and if you combine them, you need common denominators. So you would multiply n plus 1 to the first one, and for the second one you would multiply by n, top and bottom, so that now they have the common denominator. You can put them together, so you have an plus a plus b times n, n plus 1. This is not the index, it's not b sub n, it's b times n. Sorry, they look that way. But anyway, since this is a times n and b times n, I can combine them and factor the n out. So you have a plus b times n plus a over n plus 1. So a person who was very experienced in a lot of calculations noticed that you do get n times n plus 1 in the denominator if you added something like this. So next question is, well, can there be some a and b values so that this thing just looks exactly like this one? And the answer is yes, because if a is 1 and 1 plus negative 1 is 0, right, so that this becomes 0, then you get 0 times n plus 1, so you get exactly 1 over n times n plus 1, just like how you have it this side, right? So then you put 1 here and negative 1 here, and that's how you get the right side. So indeed, these two are the same, and if you are still not sure, you can multiply n plus 1 to the first one, plus, and then actually minus, multiply n to the top and bottom of the second one, and once you have the common denominators, you have like n plus 1 minus n over n times n plus 1, so n cancels and you get 1 over n plus 1. So indeed, these are the same. Okay, so now let's see how this helps. So we first rewrite this as sigma of k equals to 1 through 20 of 1 over n minus 1 over n plus 1. Well, that doesn't seem to be helpful because I don't know what to do after that, but again, remember that this is the shorthand. So think about what's the longhand. What's the longhand? It's you plug in, oh, there's a mistake here, sorry, this should have been n there, or else it doesn't make sense, right? So if this is n, you plug in 1 first, so it's 1 over 1 minus 1 half, plus then the next number for n is 2, so it's 1 over 2 minus 1 over 3, plus 1 over 3 minus 1/4, and you keep going until you reach the last one, which is 1 over 20 minus 1 over 21, because n is 20 at the last term, so this will be 20, that will be 21. And then if you look at this, now you see that there are some cancellations. You see a negative 1/2 and positive 1/2. This negative 1/3 will cancel the positive 1/3. And do you see this pattern? The first the second item in the previous one deletes the first one in the next one. So in here, this one will be deleted by the one that's preceding, which is 1 over 20. And it must have this one there. It's going to cancel. But this one doesn't have any pair to cancel, so after everything is canceled out, you see that the answer must be 1 over 1 minus 1 over 21, which is, well, 21 over 21 minus 1 over 21, so that's 20 over 21. So that is the final answer. And that's called the telescoping series.